Hello all and welcome back to video lectures on decision analysis, and now we are in chapter 5 section 5. So this will be a relatively long section. So what happens here, we look at the appendix on the calculation. So these are the M files that produce the sensitivity pictures that are the solutions for Sophie's sophomore, Susan's suite, and then their compromise. So these are rather long files and they will maybe look a little bit complicated, but if you really look at them, you see that there is nothing new. We have seen all this before. So I will go through these files now in this video lecture, although there are no explanations in the notes. Let's hope you can follow. And I noticed that there are some typos in the English language. Sorry about that. If I remember, I will try to correct them. So let us start with the Sophie's sophomore. So what we are doing now, we are looking at how this picture, so sensitivity analysis for Sophie's sophomore, how this picture was calculated. And here is the file that does the calculations, and you can download the file from here if you want to use it as a template, for example, in your own assignments, or for just want to see how it check that it works. So let us go through what's here, and I will go through now it not with Octave, but with these lecture notes. So first we have a long comment block. So what this comment block does, it simply explains what is the problem. So this is the same that's taken from the lecture notes. So it is proper description, decision matrix, decision rules. So I have simply copy pasted what is here. Then the next block comes the decision matrix. So we have two decision matrices for Sophie's sophomore. There's net worth and remaining time to graduation. So this net worth, I tried to calculate it as precisely as I could. So you should try to do the same in your assignments. So what happens, I defined variables. So SA, yearly student allowance, CS, China scholarship, CM, China moving costs, CF, yearly living costs in Finland, CC, yearly living costs in China, then yearly income in China and yearly income in Finland, then the salaries for food delivery and basic salary for multinational corporation. And then in this matrix, I looked at the yearly income, which is income minus outcome, and sometimes there are multipliers in either income or the outcome that change from scenario to scenario, and these I hope are reasonable. You can criticize them, of course, and that's the whole point. If you can criticize the reward matrix, you can criticize the solutions, but if you accept the reward matrix as this, then you have to accept the outcomes. That's how mathematics works. And again, this matrix, so there is an opening bracket and closing bracket. I have adjusted these values in the columns, so it's easier to read. Of course, it's rather hard to read. Then there is a semicolon here ending the rows. No semicolon here because it's the final row. And then the semicolons after this bracket. That means that it is a quiet assignment for R1, so it doesn't echo back the value of R1. Then the remaining time to graduation after 1 year. So these are just given the numbers. I haven't analyzed. I hope that these are reasonable numbers also. And then because this is a minimization matrix, we have to make it a maximization matrix. So I multiply this R1 into -1. So now it's a maximization rule. Then comes the sensitivity visualization. So this is something that we have seen before also. So first we have a sampling frequency, the bigger the better, but the longer the calculations take. I use sampling frequency n equals 500 and the calculations should take about 5 seconds with my computer, with my laptop, so not too long. How does this go? So we have a sampling frequency n equals 500. You can use a different value if you like. So we have P0 samples, so these are the values of P0 that they changed. So this is the lin space from 0, 1 to n. So again, let's look at Octave. So what is the lin space? 0, 1, say 9. It's like this. So 9 values between 0, the smallest is 0 and the biggest is 1, and they are equally spaced. We can have different than 0, 1. We have 2 and 10, for example. And let's say 5 values. So it's 2, 4, 6, 8, 10 then. So this is how the lin space work. So both the P0 samples and W samples are n values between 0 and 1, evenly spaced. Then we have two decision problems here. So for both reward or decision matrices, and first we fill in the so-called constant fields. So these are the fields that are the same for all W and all P0. So this we can keep outside the for loop. It makes the calculations a bit faster. So dp1 d rule is expected value EV, and its dmet decision matrix is R1. And for the dp2, so decision problem 2, d rule is the same expected value, and dp2 d matrix. So the decision matrix is R2. So these are the two rules that we are going to combine. What happens next? Then we calculate the optimal decision in the matrix Ji, where J is the W and I is the P0. So we loop around P0 samples and W samples. So first we have the outer loop. So I is the running index, goes 1 to the length of P0 samples. So this I could have written capital N also, it's the same. So P0 will be the P0 samples at I, Q0 is 1 minus P0, and then the probability fields for both decision problems 1 and 2 is this. And here note that there is this quote, single quote, that makes this row vector into a column vector. So prop has to be a column vector, otherwise it won't work. Easy to miss. Then I solve the decision problems. Now I have all the fields. So dr1 will be the d matrix dp1 and dr2 will be the d matrix dp2. Then I take the values, d values for both, and scale them, and these will be the v1 and v2, the value functions for the decision problems. So now we have the v1 value function for the decision problem 1, that's affine scaled on the interval 0, 1, and the same v2 for the decision problem 2. And then we combine them, so we have a J loop. J goes from 1 to the length of W samples. Again, this is the same as capital N. And W, I take the W samples at point J, and then I just combine them. So the vector V, the value vector V will be W times the value vector V1 plus 1 minus W times the value vector V2. So now V is the combined value function. And then I look at the maximal solution. So I take the maximum index of the V. So that's max V. So let's see how it works. It looks complicated. So there is temp and set Ji. So the reason here is that if I have a, let's look at Octave. Let's look at the vector 0, 5 to like this. So if I just type maximum of V, it will give the maximal value. But this is not what I want. I want a maximal index. So I want this solution to be 2, and this goes like this. So I call two variables from this maximum V, so val and index, value and index. So it gives the maximal value and the maximal index. So I use the maximum function this way. So the maximal value, so it will be temp, I don't use it, and the maximal index will be called ZJI. And notice JI, not IJ. This is just because the rows and columns are different from the XY plane and the rows and columns of a matrix. Just a small nuisance. So now we have this Z matrix, a big matrix, 500 times 500, n times n matrix, and then we plot it. So the plot itself is very simple. It's contour F, P0 samples, so these are the X values, W samples, these are the Y values, and Z is the corresponding matrix, Z with P0 samples and Z with W samples, so Z P0 W. And the rest here is fine tuning, so it's not strictly necessary for you to do it, but why not have your picture looking nice? So first what we do is the axis labels are rather small in the standard output, so we make them bigger. So this, what does this construct here means? It means that we set some value. So we take the GCA, it's just get current axis. I take the axis of this picture and I change the value of font size to 24. So this makes the ticks bigger and the labels bigger. Then I draw the labels for the X and Y axis. So X label is P underscore 0, and with automatically this underscore it will understand that I need a subindex, so this will be P subindex 0, and Y label will be W. Then I change the colors of the contour picture. So this is done by giving a color map. So first I define the color red as an RGB coded color. So that's of course 100% red, 0% green, 0% is blue. Green is the same as 0% red, 100% green, 0% blue. And then the color map is a matrix where the first row is the first color, second row the second color, and so on. So the first row is the red, second is 0.6 times red, so this will be a dark red. Next row is green, and the last row for the last color is dark green, so 0.6 times green. And finally, I set labels in the picture. So this is very important, so otherwise it's rather difficult to read what color means what. And this I've done just manually. I check the matrix Z, so I figure out which area is which. So how this text goes, so this is the X point and this is the Y point, so where the text will be written in the picture. So X 0.4, Y 0.5, I put a label A1, and then I will still say that it will be the font size 24, so otherwise it's rather small, this A1, so now it will be relatively large text. And the same for A2, A3 and A4. So that's it. Then there is a final point. So if your PDF driver works, in Windows I think it does not work. Let me comment on that a little after a while. So if I uncomment these lines, so then it will print the picture here into a PDF file named this and in the landscape format on the paper. If your PDF driver doesn't work, then you can change this extension to something else that works. For example, JPG should work. So that was the file for Sophie Sophomore that plotted this picture. Let us then look at the file for Susan Suite. So Susan Suite had this picture, so the next file shows how this picture was calculated. And this is very similar to the Sophie's, so I will go this through, and again you can download this for your use from this link. So what is the Susan-Suits problem. So first we have a description of the problem, basically from the lecture notes. This should be world. I think that I copy pasted it, so it messed these words for some reason. This was maybe a ligature that did that. Sorry about that. If I remember, I will correct these typos. So the same thing first with decision matrix. So there is only one decision matrix for Susan, and that was the yearly salaries after monthly salaries after 3 years. So here it is. I took some time, and there were some reason that I came up with these numbers. I listed there in the comments what are the arguments why these numbers should be reasonable. Again, in your assignment, try to argue why the numbers are reasonable and try to have as reasonable numbers here as possible. Again, as I said, all the else in this technique is just mathematics, but this is where you have to be creative or reasonable. So the decision matrix has to be good, and then the analysis is good, and if the decision matrix is bad, then the analysis is bad, of course. And then we go to the visualization and constant fields. So we have two decision problems. There's one decision problem with the decision rule expected value, and another decision problem where the decision rule was regret avoidance. So constant fields for, let's call the decision problem 1, the one with expected value. So the decision matrix is R, and the D rule is expected value. So these are what we can, don't depend on P0 or W, so these we can just tell, but not others. Then the decision problem 2, which is the regret aversion. So this is non-stochastic rule, so it doesn't depend on the probabilities P, especially it doesn't depend on the polar pandemic probability P0, so this we can actually calculate completely. So what we do, decision problem 2, D matrix is R, decision problem 2, D rule is regret. Then we solve it, because these are the only fields that we need. Then we take the D values and call this V2. So there are the D values now, but this is a minimization type problem because it's regret avoidance. So we want to make it a maximization. So then we multiply by -1. So V2 will be minus V2. And finally, we want to combine this with another rule. So we have to have this V2 scaled. So we have V2 equals scaling V2. So now we have the value function for the problem 2 scaled affinely on the interval 0, 1. And then let's go to the for loops for P0 and W. So first we need, as always, a sampling frequency. The bigger the better, but the calculations take more time. And I've used n equals 500. This gives rather nice smooth picture, and the calculations take approximately 3 seconds, so not too long. So how do the calculations work? The same as always. I take the P0 samples and W samples, values from 0 to 1, n of them evenly spaced. Then I have an outer loop for I for the P0s. So then the P0s will be the P0 sample I, Q0 1 minus P0. Decision problem 1, I need the field prop there, so it depends on P0, and it's like this. Again, the single quote here to make it a column vector. Now I have everything for dp1, so I can call dr1 will be the D matrix dp1. So it's the solution of the problem 1. And then I take v1 to be the scaled version, so scaling of decisional result 1 D values. So now v1 is on the interval 0, 1 as it should. And now I have v2 already I had before the loop. Now I have v1. Then I go to the j that goes from 1 to the w samples. Again, length w samples is capital N. I could have used that. I take w to be the value of w1 sample, so this will be the number between 0 and 1. And then here is the combination. v vector will be w times v1 vector plus 1 minus w v2 vector, and this is the same as we've seen before. So I take the maximal index of v, so maximum v, so temp. So this goes to temporal variable I don't use. This is the value, and this is the index. And finally, we have the picture, and I will not explain this now because this is exactly what happens here is exactly what happened in the Sophies file. The only difference is that there are only two optimal solutions, A1 and A2, so the text there is no A3, A4, because only A1 or A2 will be optimal for Susan. So that was for Susan, and then finally we have the combination. So Sophie sophomores and Susan Suits compromise. It's here. It's rather long, but it's the same idea as always. So you can download it from here if you like. And let me go through on a very quickly this, because this is all we have seen before. Now it's just, of course, we have many rules. So again, a big comment block explaining what's going on. This is a copy pasted from the lecture notes. Then decision matrices. Now we have many decision matrices. We have two Sophie matrices. So this is from the Sophie's file, but now I call it RSO1 and RSO2 for reward matrix Sophie 1, reward matrix Sophie 2. Again, Sophie 2, this is a minimization, so we have to turn it to maximization, so we have to multiply it by -1. And then Susan's decision matrix RSU now called, and this is taken from the Susan files. Then comes the visualization. So the decision problems constant fields. I first have, so decision problem Sophie 1. D matrix is the decision reward matrix SO1. D rule, expected rule. Then decision problem Sophie 2, D matrix. The other D matrix are SO2, and D rule again EV1. Then we have two problems for Susan also, so decision problem SU1 and decision problem SU2. They are the same matrix RSU, but the first problem has the expected value rule, and the second problem has the regret rule. Then we can calculate the regret rule completely. So decision result Susan 2 is the decision matrix or decision problem Susan 2, which is given here. Only these two fields are needed because the regret rule. So regret rule was a minimization, so we have to turn it to maximization. So I multiplied by -1, and then I scale it. So these are the constant fields, and rest of the fields we need the for loops for different w's and different p0s. So again, we start with the sampling frequency. Lots of typos, sorry about that. The bigger the better the picture, but the longer the calculation take. And for n equals 500, that gives us a nice picture. The calculation take 5 seconds in my computer. Of course, your calculation time may differ. And again, then the sample points, P0 samples and W samples, lin space, n values between 0 and 1. Then we have the I loop for P0s. We take the P0s. P0 will be the P0 samples I, so this is the value between 0 and 1. Q0, 1 minus P0. And then we have three problems where we need this probability. So Sophie's 1, Sophie's 2, and Susan's 1. And it's the same for all of them. We give this probability vector and note these single quotes there. That makes the vector a column vector as it should. Now we have everything we need, so we solve this SOFI 1, SOFI 2, and Susan 1. Remember that Susan 2 has been solved already. What we do then we scale the values, SOFI's values, and combine them. And this is, remember in the notes, so the W now will be the combination between Susan and SOFI, so we cannot use the W as a free parameter for SOFI, so we chose that SOFI takes the W equals 1/2, and so does Susan also. So here it is, the SOFI's rule will be 1/2 times SOFI rule 1 plus 1/2 times SOFI rule 2, and then we scale the SOFI rule. Always remember to scale when we are combining rules. Then the Susan rule, the same, so the Susan 1, we take the scaling or additional result Susan 1 of the d values and combine the Susan rule 1 and the Susan rule 2 or the Susan value functions with W equals 1/2, and remember always to scale the rules. And then we combine the SOFI rule VSO here and the Susan rule VSU here with the value W. So this is the inner loop. J goes 1 to the length of W samples. W will be the value of the W samples at the point J. So this is a point between 0 and 1. Just affine rule W equals W time V equals W times V SOFI plus 1 minus W times V Susan. And the same thing, so here I have forgotten, so this is the Finnish word means garbage. So this is the temp variable. It doesn't matter what I call it, I just have to assign it to somewhere so I can access the latter output value, which is the maximal index. And that's it. And then we have seen this many times before. So this is the picture, how it's drawn. So here is the drawing command. So this draws the picture. Then we set the scale, the size of the axis labels bigger. X label and Y label are given. So these are the colors that I define, and the color map will be, there will be 3 colors actually. So there will be red, yellow, and green. So this is the matrix that gives the colors of this contour picture, and then I just put the text there. I check manually the places X and Y where I have A1, A2, and A3, and then the font size for them is 24, otherwise they're rather small. All right, so this is the longest code we have in this node. So if you understand what's going on in this example SOSU.m, then you understand everything. So that's the longest that has almost all the intricacies and complications we have in our codes. Thank you for listening. See you in the next video lectures. Bye.